previous PhD student, Wanyan Rong. So this is basically the master's thesis from Delena Funicular. So she graduated in 2022, and she would be a great asset if anybody ever wants to recruit her. So seismic compression, this started to become a term in the early 2000s after following the Northridge earthquake. It's basically the accrual of contractive volumetric strains associated with cyclic shearing during earthquake events. Even though this has been proven to cause a lot of damage, there are not really very strong models, and there's also not a very clear database of information on this topic. I started working on this in the early 2010s. My previous PhD student, Majid Gayoumi, did some centrifuge tests, and we developed a very empirical model. And so the goal of this particular project is to try to have a more physics-based model where we're able to capture all of the different interactions between the different pore fluids, pressurization, and the volumetric response. So why is this important? Many geotechnical systems are meant to be unsaturated by design, so things that are built up above the ground surface. Any small deformations of these systems can have big implications on the performance of the superstructure, especially if you're looking at MSE bridge abutments, road and rail embankments, and retaining walls. And even if you're using dense soils in these materials, they're still going to show contractive strains during cyclic shearing. Even though if you do monotonic shearing to large strains, there's going to be dilation, but during cyclic shearing, you usually see densification of these materials. So this is a project focused on unsaturated soils, so we always need to start with soil water retention curve is our main reference point. This is quantifying how much water is in the soil and then the energy state in the soil, which is the matrix suction. And we're focusing on one specific regime of the soil water retention curve, the funicular regime. A lot of work has been done in the capillary regime that is close to saturation, where people were looking at liquefaction of nearly saturated soils. So we're looking at a little bit drier, where the water phase and the air phase are both continuous. But those water-filled pores and air-filled pores could pressurize when you have the collapse of voids during shearing. There's also some complicated unsaturated soil mechanics things where when you contract the voids, you're reducing the volume of pores, so the degree of saturation goes up, and you're usually going to be following some sort of a scanning path from your initial points that are shown in red. So we'll talk about that a little bit more when we start to talk about the modeling. Another tricky thing when you look at shearing of unsaturated soils is the drainage conditions. From the liquefaction perspective, most people are thinking about undrained single-phase materials, but suddenly now we have air and water. So we could have both of them being drained, one of them being drained, or both phases being undrained. And that's the focus of our study here. So there have been some previous studies on cyclic shearing of unsaturated soils in undrained conditions, but these are mainly very close to saturation, 80% degree of saturation or above. So we're looking a little bit drier than that. So what happens when you cyclically shear these unsaturated materials? The voids that are filled with air are going to collapse and densify. We're going to pressurize the pore fluids, either due to collapse of the voids or just overall decrease in volume. If we have differential pressurization between the air and the water, we're going to have changes in suction. So suction is that point value on the soil retention curve. The degree of saturation is going to evolve. As the voids decrease, then the degree of saturation is going to have to increase. So if you have changes in degree of saturation and suction, those together are incorporated into the effective stress. And the effective stress is going to affect your shearing properties, like the bulk modulus, the shear modulus, and those are going to affect the subsequent cycles of shearing. So effective stress, there's many different relationships that you could use for this. I use the approach of Ning Lu, where you add the suction stress to your net stress. The suction stress is the product of your degree of saturation and suction. So both of those are changing. It's the product of those two that is going to be changing your effective stress in your soil. Sands, which are the focus of this particular study, have a suction stress curve that looks kind of like a U shape. This is why sandcastles are strong when they're in the middle range of degree of saturation. When you're completely dry, it's like a powder. When you're completely wet, it's like a mud. But in the middle degree of saturation, you're going to have a strong condition. So our hypothesis at the beginning of this is that if you're in this middle range of degree of saturation, you're going to have some resistance to seismic compression. However, that's not always necessarily going to happen, because if there is water and air, they could pressurize in a certain way that they could lead to a decrease in effective stress. So it's a very complicated coupled process. As I mentioned, the effective stress is directly proportional to your small strain shear modulus. So if the effective stress goes down, your shear modulus is going to go down, and the material is going to get softer. So there's been some work on this a lot at UCLA by Jonathan Stewart's group. They found for silty soils that there is a very clear effective degree of saturation, but for sandy soils they didn't see a very clear trend. However, some of their tests had some effective compaction-induced soil structure superimposed on top of the effective degree of saturation. My previous student, Majid Gayoumi, did some centrifuge tests where he had constant rates of infiltration, which changed the degree of saturation, and then he shook a centrifuge test. And we saw, as the degree of saturation changes, we saw a U-shaped trend in the seismic compression with a minimum value at this middle range of degree of saturation, so following the suction stress trend. But one problem with the centrifuge test is that we don't really know what the drainage conditions are. It's just what it's going to be when you shake it. So that's one of the reasons that my previous student, Wen Yang, did a series of undrained and drained cyclic simple shear tests where we could very carefully control the drainage conditions and measure independently the suction, the pore water pressure and pore air pressure to calculate changes in suction. So here's some examples of the tests that he performed for some different initial degrees of saturation. For his tests, he saw a smile shape as well, but this is because the volumetric strain is aligned downwards in this figure. This would actually be a frown if you compared it with the results from Gayoumi. So it's the opposite trend with initial degree of saturation, but we hypothesized that this could be due to the effects of fully undrained conditions in these tests. So one of the reasons that we wanted to do some modeling was to confirm if that happens. There's also a very practical empirical approach to estimate seismic compression from Jonathan Stewart's group. He took that trend between vertical strain and shear strain and put it together with the outputs of a site response analysis. So if you have your shear strain profile induced during an earthquake, you can empirically figure out what the seismic compression is going to be. So this works, but it's still more of an empirical approach. A step up, a more semi-empirical approach is the approach from Majid Gayoumi, where he basically took the trends for some empirical approaches for dry soils and post-liquefaction reconsolidation from saturated soils, put them together in a sum form to predict seismic compression. And you can see that these are very long empirical equations with many variables that are hard to determine in the laboratory, like the blow count and other things like that. But these work, and he was able to get a good match with his data. But the problem with this empirical methodology is that really if you choose any of the parameters that you choose could have a big effect on the results of your model. So we wanted to come up with this new model, which was the focus of this project. And we decided to start with the UBC sand model, basically a hyperbolic model that has some aspects of elastoplasticity. And we wanted to incorporate the fluid pressurization effects from Boyle's and Henry's law. And we wanted to come up with an approach to independently figure out what the pore water pressure is going to be from the pore, estimated from the pore air pressure. So let's go through how the model works. So in a cyclic simple shear test, you have a Mohr circle that's shown here in black, and it's basically expanding out to the blue circle and coming back to the black circle, and then going back to the blue circle as you shear the specimen left and right. So every time that you expand that circle from the black circle to the black circle to the blue circle, you're having plastic shear strains. So anytime you're having plastic shear strains, you're generating volumetric strains through a flow rule. So we used these simple approaches defined in the UBC SANT model. We won't go through all the details here. But the first step is to fit a hyperbolic model to your stress strain curve to determine the parameters of that. And the main parameter that is controlling the shape of this is the shear modulus. So the shear modulus here is dependent on the effective stress state. So if the fluid pressures are changing, they're going to be changing the effective stress, they're going to be changing the shear modulus, and it's going to change the shape of your stress strain curve. When you're doing the cyclic loading, you need to have equations for the full stress strain loop. And these are just how we have the initial shear modulus at small strains, and then as plastic strains occur, you start to have a plastic shear modulus. One thing that we did in our model is that you only accrue shear strains when you have plastic, you only accrue volumetric strains when you have plastic shear strains. So whenever you're loading out in red, you have seismic compression, but then under unloading, you don't. So you end up having a cumulative plastic strain looking like this. You could very simply use the phase relationships to get your degree of saturation from your estimated volumetric strain, and then also use all of your ideal gas law, Boyle's law, etc. to estimate your air pressure from the volumetric strain. So once you have the air pressure, we used an approach where we use those scanning paths from the solid retention curve to estimate the water pressure. To estimate first the suction, and then using the suction and the air pressure to get the water pressure. And then finally, we put all those together into the effective stress equation and update our modulus and go to the next loop. So we compared the model with several different experiments from the cyclic simple shear tests of Wanyang Rong, and we calibrated it for the sand. So first we used some drained loops to get our basic parameters of the hyperbolic model. And we had some parameters that are governing the shape of these scanning paths. And at the end of the day, we had 8 parameters in the model. Everything else are constants. So the estimation of the pore air pressure is completely based on constants. So just some typical matches. The black curves are the predicted values from our model, and the other two are a pair of experiments with similar initial conditions. It's not perfect, but from this simple model, we're able to capture these evolutions in seismic compression with number of cycles. And just some different trends here. In the experimental data, we saw that the seismic compression was really continuing on as you go to very high numbers of cycles, whereas the model kind of reaches an asymptote. There is still a very clear effect of the initial degree of saturation. So because of that, we only made some comparisons at small numbers of cycles. And you can see some of the comparisons between the model and the data. It doesn't show the best fit overall, but generally I think it is starting to capture the data. So there's some reasons for why the model is not giving a good fit. There's potentially some creep or pore fluid redistribution in the experiments that are causing this deviation at large numbers of cycles. The model, even though there's an effect of the initial degree of saturation on the pore air pressure generation, when you go to large numbers of cycles, the pore air pressure generation is almost the same for all of the specimens. And then in the tests, sometimes we were never exactly centered around the plus and minus 1% cyclic shear strain. The shapes of the loops were never fully hyperbolic like we assumed in the model. So there are some possible experimental reasons for why the data did not exactly match the model. But at the end of the day, I think using some of these unsaturated soil mechanics concepts can help us have a physics-based understanding of some of the evolutions between these different variables. I think there's a lot of future research that we could do on this topic. And I was happy with the results from a master's thesis on this complicated topic. So I probably will need to leave quickly after this, but if anybody wants to email me, I'm happy to discuss the topic more. So thank you.